Hello and welcome. My name is Aidan Boyd, and today I'm presenting the paper CYBORG, Blending Human Saliency into the Loss Improves Deep Learning-Based Synthetic Face Detection. So the motivation for this work is around the question, can human saliency information be included in the training procedure of our deep neural networks to help the generalization capabilities of these? And the way we want to investigate this is by incorporating human saliency information into the loss function. And the task that we're going to apply this to is open-set synthetic face detection. So to collect the human saliency information, we presented images to users and asked them to identify whether it's a real or a fake face, an authentic or synthetic. Further from that, we asked them to annotate on the image with their mouse regions that supported that decision. We ask multiple subjects to annotate the same images, and that enables us to generate human saliency maps, as seen in the figure in figure C. Figure D is a heat map representation of that human saliency map overlaid on the image. So we see people are focusing on the eyes, nose, and mouth. So what we do is we create a thing called CYBORG loss, and CYBORG stands for ConveY Brain Oversight to Raise Generalization, and is basically a combination of traditional classification loss, categorical cross-entropy, and this new element, the human saliency loss. And human saliency loss is the distance between the human saliency map, like we defined in the previous slide, and where the model is currently looking, as defined by class activation mapping. And we penalize large distances between these. So we're trying to guide the network towards human-defined regions of saliency, to look where humans are looking. Our experimental setup involved 100,000 authentic images across 2 public datasets and 600,000 synthetic images across 6 different GAN sources, only one of which is available during training. So 5 of these GAN types were unseen during training, hence the open set synthetic face detection approach. We also train these approaches on 4 out-of-the-box networks architectures: DenseNet, ResNet, Inception, and Exception. And the idea here is to just make sure that any observations that we see are not architecture specific, and that this loss function can be applied to any network. And for each of these, it's the exact same training procedure. The first result we see is actually a protection against overfitting. We see the blue line here is when you train only with the classification loss, without this human saliency component, and we see that the validation accuracy hovers around 80%. However, when we add this, only difference is that we add this human saliency component, the validation accuracy increases to around 95%. On the test set, we also see a significant performance increase when using CYBORG versus when just using classification loss alone. Additionally, we see that using CYBORG does better than even increasing the training set size by 7 times. So each sample with human saliency is worth more than 7 samples without human saliency. In conclusion, the addition of forced annotation also increased human accuracy, which is explained in the paper. We see that CYBORG increased the performance on the test data, and we also saw that it increased the performance so much more than even when we increased the training set by 7 times. One of the side effects we saw is also it protected against overfitting. Thank you for listening, and hope to see you at the poster.